Hello, everybody. Welcome to this second session of the webinar series in which we will speak about PV standards used for PV module characterization and certification. In the first part of the presentation, I will speak about main IEC qualification standards used for PV module certification, and then my colleague Javier will explain the measurement of the IV curve of mono and bifacial PV devices. First, it is important to define what is certification. To certify is to declare compliance against a standard or a procedure. And why it is important to certify the PV modules? Not only because it is a requirement of the market for commercialization, but also from the point of view of the final user to feel confident on the quality and safety conditions of the product that he or she has bought, and to avoid risks during installation and operation. Also, from the point of view of the manufacturers, it is important to certify their products to show reliability against common rules and also to define the scope of their warranties. Who is who in the certification process? There are three important parts in certification. We have the standard, the testing, and the certification itself. The standard is where the requirements of the product that the product must fulfill are laid down. There are many organizations around the world developing standards for the PV sector. In this presentation, we will only explain the main IEC standards for PV modules. Then we have the testing. The testing is performed by an accredited laboratory. The laboratories also must show competence for testing and calibration according to their own standard, the 17025. The accredited laboratories are audited periodically, and also they have to compare their results with other accredited laboratories. And finally, we have the certification bodies, who are the organizations that who issues the signed document based on the test report of the laboratories. There are different types of certificates. We can have only a certificate of compliance when only the tested samples are inspected, but then it is possible also to audit the manufacturing factories, and then the certification body can issue a product certificate. The most relevant IEC standards used in for PV modules are the IEC 61215 to qualify the performance of the PV modules. Then we have the safety qualification standard, the 61730, and then we have the IEC 60904 series, where the characterization of PV devices from different characteristics are performed. Here we can see the structure of the safety and performance standard. The 61215 has two parts. The first one describes the general requirements for all technologies, and then these two parts describe the specific requirements for depending on cell technology. And then we have the part 2 of the standard, where that describes the test procedures and are valid for all device technologies. The 61730 has also two parts. The first one is related to the requirements for construction, and the part 2 is related to the requirements for testing, and the safety standard is valid for all kinds of technologies. The IEC 61215 standard is designed for design qualification and type approval of PV modules for terrestrial application, has comprises two parts. One of them is related to marking and documentation, a very important section of the standard, where it states the label, the electrical parameters that must appear on the label of the module, and also all the information that the manufacturer must provide in the instructions manual for installation and operation of the PV module. And then the other important part of the standard is the one that describes the testing. The philosophy of the standard for testing is first, initially there are performed some diagnostic tests, then the modules are subjected to some agent tests, and the diagnostic tests are repeated to see the degradation that the module has suffered. There are also some characterization tests, and then a pass or fail criteria is applied. Here in this slide, we can see an overview of the test sequences of the standard 61215. Here, 10 modules are inspected initially, and the initial diagnostic tests are performed. Then we have the characterization and degradation test, and finally we have also a diagnostic test to apply the fail and test criteria. The objective of this test sequence is to determine the electrical and thermal characteristics of the modules and to show within reasonable constraints of cost and time that the modules are capable of withstanding prolonged exposure in moderate climates. Now we will briefly explain its test of the standard. It's MQ test, module quality test. We start with the visual inspection to detect any visual defects in the module that could adversely affect the proper operation of the module. Here we look for there are a list of major defects defined in the standard, so we have to check that there are no air bubbles or delaminations, nor broken cells, or any other mechanical defect that could adversely affect the module. Then we have the MQT2 for maximum power determination. This test is repeated also at the end of the sequences to check the degradation of the power across the different sequences. Then we have the insulation test under dry conditions to determine whether the module is sufficiently well insulated between live parts and accessible parts. A high voltage is applied between the frame and the internal circuit of the module to verify the insulation resistance is high enough. Then we have the MQT04 test, is the measurement of temperature coefficients. Here, the IV curve or the different electrical parameters, the main parameters of the IV curve are measured, like the short circuit current, the open circuit voltage, and the maximum power, and the variation with the temperature is measured. Here we can see measurement of the nominal module operation temperature. Usually the modules are rated at standard test condition. So we have the power value that the modules will provide under standard test conditions. That is at 25 degrees centigrade of temperature and 1000 watts per square meter of irradiance. The standard test conditions are very different from real world, and here in this test, what we want to determine is the real temperature at which the module will operate in the field under more realistic conditions. And therefore, this parameter is also very useful when comparing the performance of different module designs. Then we have some other characterization tests. The MQTOC is the performance at standard test conditions, because the first one, the MQTO2, for maximum power determination, can be performed within a range of irradiance and temperature conditions. But here we have to measure the performance of the module exactly at standard test conditions and also at the temperature measured in the previous test, MQTO5. Then we have to perform also the MQTO7, which is the performance of the module at low irradiance. That is 200 watts per square meter, 25 degrees centigrade of cell temperature, and the light spectral distribution according to the spectrum AM 1.5 global. Then we have the MQT8 test, the outdoor exposure test. The purpose of this test is to make a preliminary assessment of the ability of the module to withstand exposure to outdoor conditions and to reveal any synergistic degradation effect which may not be detected at the laboratory conditions. The next test is the MQT9, the hotspot endurance test. The purpose of this test is to determine the ability of the module to withstand hotspot heating effects provoked by faulty cells, mismatch among the cells, shadowing or soiling. Here we have to expose the module under the worst shadowing condition to check that the bypass diodes and any other artifact to protect the module is working properly. Here we have the MQT10 test. Is the UV preconditioning test. It is only a preconditioning because here the module is exposed to a UV radiation of 15 kilowatts hour per square meter in the UV range. UVA and UVB dose is applied at 60 degrees centigrade module temperature. This dose is very reduced and is only a condition previous to applying the thermal cycling and the humidity freeze test. And the purpose here is to identify those materials and adhesive bonds that are susceptible to UV degradation. This is the MQT11 thermal cycling test. Here the modules are submitted to repeated changes of temperature from -40 degrees centigrade up to 85 degrees centigrade. Depending on the sequences, only 50 cycles are applied or 200 in the other sequence. And the objective here is to determine if the module will be able to withstand thermal mismatch, fatigue, or other stresses caused by repeated changes of temperature. This is the humidity freeze test, where the modules are submitted to high temperature and high relative humidity periods of at least 20 hours at 85 and grades centigrade and 85% of relative humidity, followed by below zero temperatures of up to minus 40 grades centigrades. And this cycle profile is repeated 10 times. And the objective of this test is to check the ability of the module to withstand the effects of high temperature and humidity conditions followed by sub-zero temperatures. This is not a thermal shock test. The dam heat test, here the module, during the dam heat test, the module has to withstand during 1000 hours, that is 42 days, submitted to the conditions of high temperature and high relative humidity. The purpose of this test is to determine the ability of the module to withstand the effects of long-term penetration of humidity. Then we have the mechanical test, the robustness of termination. Here, different parts of the are tested in the module, the retention of the junction box and also the test of cord anchorage to test the cable of the module. And here the objective is to determine that the termination, the attachments of the cables to the body of the module will withstand the stresses that are likely to be applied during normal assembling or handling operations. Here we have explain the wet liquids current test. Here the module is placed inside a bath, as you can see in the picture. And the objective is to evaluate the insulation of the module under wet operating conditions and verify that moisture from rain, fog, dew, or molten snow does not enter into the active parts of the module circuitry, where it might cause corrosion, a ground fault, or a safety hazard. Then we have the static mechanical load test, the MQT-16. Here, a uniform load is applied from the front and rear sides of the module. The load applied is at least 2,400 pascals. And the purpose of this test is to withstand, to check if the module can withstand a minimum static load caused by wind or snow accumulation or ice. This is a picture of the hail test to verify that the module is capable of withstanding the impact of hail. 11 ice balls are launched against the module at different parts, and typically the ice balls are of 25 millimeters of diameter and at the speed of 23 meters per second. Finally, we have the MQT-810 bypass diode testing, where the bypass diodes of the modules are assessed to check that the thermal design is okay for the final application, and to check that the hot spot, that the module is properly protected with the bypass diodes from the hot spot effects. And the MQT-19 is a light-induced degradation test, because all the modules need to be electrically stabilized. For this purpose, all modules are be exposed to a defined procedure. This test changes depending on cell technology, and all the modules are exposed to a defined procedure, defined in each subpart of the standard, and the output power is directly measured afterwards. This procedure has to be repeated also at the end of the sequences for all thin film technologies, and the power output is measured under stable conditions. Here we can see again the test sequences, but with the diagnostic tests included in every degradation test and also at the end of the sequence. The pass criteria of these standards comprehends different parts. One is that the samples should not exhibit any open circuit during the tests. The visual defects should be only minor defects. If there is a major defect, the module design will fail the qualification. Here are some examples of defects, visual defects on PV modules. Most common one are the laminations or yellowing of the encapsulants. One of these defects can be considered minor, and other when the air bubbles contact directly the frame, the outside, it would be a major visual defect. And then there are here some examples after a mechanical load test. These are mechanical defects. And then another pass criteria is electrical safety. We have to check as a final diagnostic that the insulation of the module under dry and wet conditions fulfills the requirements of the standard. And finally, in this standard, as it is a performance standard, we have to check that the output power of the module is that the one that the manufacturer declares in the labels. Here we have initially a criteria, a pass criteria for power output. And then at the end of the test, we have another criteria that the modules must fulfill. If two or more modules fail, then the design fails the standard, and it has to be repeated again with some design modifications or whatever. But if only one module across one sequence fails, two additional modules shall be subjected to the entire series of tests of the respective test sequence. And again, both modules should pass to gain the certification. Now I will give a brief insight on the safety standard qualification for PV modules. The part 1 of the standard specifies and describes the fundamental construction requirements for PV modules in order to provide safe electrical and mechanical operation. There are a lot of characteristics that must be checked about the materials and components of the modules. Some of the properties of the materials and components of the PV modules declared in part 1 of the standards are checked through testing in this part 2 of the standards. Here we have the test sequence for 61730, and although there are many tests here, most of them are the same than for the qualification test standard, the performance. So both standards can be carried out in parallel in a combined test sequence. The test sequence of this second part of the standard for the safety is thought to detect the potential breakdown of internal and external components of the PV module to avoid the risk of fire, electric shock, or mechanical problems that could cause personal injury. Here are listed the environmental stress test in standard 61730. 4 of them are common to the 61215 standard, and 2 of them are new, the cold conditioning and dry hot conditioning. Here the module has to be in the cold conditioning during 48 hours at minus 40 degrees. And in the dry hot conditioning, the module has to be at 105 degrees centigrade during 200 hours. Those tests are optional tests only to reduce the pollution degree of the materials. Those are the general inspection tests. The new ones are the insulation thickness to be performed on polymeric insulation sheets. The MST module safety test 5, durability of markings, is performed to check that any marking shall be durable and legible during the test. Compliance is checked by inspection and by rubbing the marking by hand. And then we have the sharp edge test to check that the accessible PV module surfaces are smooth and free from sharp edges. These are the electrical shock hazard tests. These tests are designed to assess the risk to persons from contact with active parts of the PV module. The first test is the accessibility test. Is used to look for if the module is well protected against accessibility. Here we use this proof to simulate a human finger. Then we have the cut susceptibility test. It is used to determine whether any front and rear surfaces of the PV module made of polymeric materials are capable of withstanding routine handling and during installation and maintenance without exposing personnel to the danger of electric shock. We use this text fixture. And then we have the MST 13. The purpose here is to verify the continuous path between accessible conductive parts in direct contact with each other, as it happens in the different parts of the metallic frame. And finally, the new one shock hazard test is the impulse voltage. The purpose here is to verify the capability of insulation of the PV module to withstand over voltages of atmospheric origin. The impulse applied here has the shape shown in the picture. The fire hazard tests assess the potential fire hazard due to operation of a PV module or failure of its components. The temperature test is designed to determine the maximum reference temperatures for various parts and materials used to construct the module. The fire test, MST23. The PV modules may be exposed to external fire conditions and therefore should be tested for the fire resistance characteristics when exposed to a fire originated from outside of the PV module. Through this test, we check the fire resistance class of the PV module. The ignitability test determines the capability of the module to resist direct small flame impeachment. And the reverse current overload test is intended to determine the acceptability of risk of ignition when the module is operating under reverse current fault conditions. The mechanical stress tests are thought to minimize potential injury due to mechanical failure. The first one is the module breakage test. The purpose of this test is to provide confidence that risk of physical injuries can be minimized if the module is accidentally broken. Here we can see the test fixture and the impactor used for impacting the module. Then we have the MST33. Here, the components of the module, such as screws or nuts, transmitting contact pressure, shall be tightened and loosened at least five times. Then we have the MST37, the material grip test. Here, this test is intended to validate that the materials used in the PV module will not show creep or loose adhesion when operated at highest temperatures that the module normally experiences in the field. And finally, we have the peel and lap shear test. They are carried out to check if the quality of the insulation of specific insulation materials called cemented joints provide confidence regarding the durability of the adhesion between different layers. Here we can see the test fixture used at center to carry out the peel test. The pass criteria for the safety standard includes visual defects, like the ones defined in the 6.12.15 standards, and also electrical safety requirements under wet and dry conditions both. Here we have to remind that the withstanding voltage test was carried at a higher voltage than in the performance standard. Here, the voltage applied for this test is 2000 volts plus 4 times the maximum voltage systems, and the module must do not show the electric breakdown, and the insulation resistance shall be higher than 40 mega ohms per square meter. No power requirement is a pass criteria here. Thank you very much for your attention, and now I leave the floor for my colleague Javier. You can start when you want. Thank you.
Thank you, Annabelle. Hello, everybody. I'm going to talk about maximum power determinations of PV modules. The measurement of PV current voltage characteristics is described in the standard that Annabelle has mentioned before, is the IC 60904 Part 1. First thing I want to mention is that there are many different conditions in which the maximum power can be measured. Most typical is the STC, is the standard test conditions, 25 degrees, 1000 watt per square meter, and the spectral distribution of AM 1.5. But you can also measure at different conditions, and at NMOD, for example, at 800 watt per square meter, at low irradiance, which will be 200 watt per square meter. There is a standard which describes different possible conditions of temperature and irradiance. And then another important point is that if you want to verify the degradation, like for example in the 6.12.15, it's important to do the measurements always at the same conditions. That way you can increase the reproducibility of your results. So which equipment do we need for measuring? We need a radiant source, so we need light. It can be natural sunlight or it can be a solar simulator. You need a PV reference device in order to measure the light. You need something to measure the IV curve, so an electronic load, for example, to measure the current and the voltage. You need some temperature sensors for both the module and the reference cell. You may need something to modify the temperature of the device under test, of the module. You might also need some optical filters for modifying, for reducing the irradiance. For outdoor measurements, you also could use a solar tracker in order to position the sun, position the module, sorry, perpendicular to the sun. And you should use also an spectroradiometer to know the spectral distribution of your light. So regarding the radiance source, usually in the labs, a sun simulator is used, and usually is a flasher. It has to be characterized according to this standard. And the result of the characterization is a simulator class that is defined by 3 letters. For example, AAA or CBA or whatever. Which is the meaning of the letters? The first letter is related to the spectral match. It can be A, B, or C. This means how close is your spectral distribution to the sun, to the spectral distribution standardized for the sun. The second letter is related to the spatial uniformity. In every point of the test plane, you have to have the same amount of light. And the third letter is related to temporal stability. So along the duration of the measurement, the amount of light has to be the same. So you also need a reference device. There is another standard for the definition of these requirements. Important aspects of these are the sensitivity, which is the output at 1000 watt per square meter. It must be linear. It's important to know the temperature coefficient and the spectral response, and it should be used, and it should be spectrally matched to the module. You also need something for measuring the IV curve, like an electronic load. You have to do a voltage sweep and to measure the voltage and the current. Important aspect here is that the electrical connection has to be done using 4 wires in order to reduce the effect of the connection of your equipment to the module. Other important aspects, the incident angle should be normal incidence. That's why I mentioned that solar tracker could be used for outdoor measurements. This has to be done, or this should be done, in order to avoid effects related to the angular reflectivity of the samples. And you will need a spectroradiometer as well in order to compute spectral mismatch, especially in case of the module and the reference cells are not spectrally matched. For example, in this case, we have the spectral distribution of the sun, the spectral distribution of one simulator, and the green line will be the spectral response of a cadmium telluride module, and the red one will be the spectral response of a crystalline silicon. So in this case, you will need to compute the spectral mismatch, for example. So which is the procedure? Well, I have mentioned before that you have to do a voltage sweep. During the measurement, you change the voltage. The current will change as well, and you have to measure both values. So you get the IV curve. Afterwards, you need to do some temperature and irradiance corrections in case you want to give the results at some different conditions, for example, STC. You need some parameters here. You need the temperature coefficients. You need the series resistance. In this standard, there are several procedures described. Some examples. Here we have the IV curves of a module measured at different irradiances. We can see here this is the source circuit point, and the source circuit point is decreasing as well as the with the irradiance, but the open circuit voltage doesn't change a lot. In this example is the IV curves of a module measured at different temperatures. And in this one is, I don't remember exactly which one, but it's a module submitted to a climatic test, and we can see that the module suffered a clear stress and a clear degradation, especially at the end. Some aspects, important aspects related to thin film modules. There are some technologies like cadmium telluride or CIGS, for example, that have metastable effects. So that means that when the module is shipped to the laboratory, when we get it out from the box, the maximum power is different than under stabilized conditions. For example, in this case, the blue line will be a maximum an IV curve of a module, and before the preconditioning, just out of the box, and the red line will be after the preconditioning. So we have to install it under light during some time, and afterwards we get the real value of the maximum power. That's an important point. In the case of amorphous silicon, you have to take into account the Stable-Brodsky effect or the light-induced degradation, and you can also have seasonal variations. So, for example, here is an amorphous silicon. At the beginning of its life, the module, the maximum power was higher, and then it decreases with some exposure time under 1,000 watt per square meter. So it's important in these cases to stabilize the modules before the measurement. Another important aspect is that we have seen that these technologies are not stable, but we need to use a spectrally matched reference cell. So usually a crystalline silicon reference cell with some optical filters are used. So it's important to perform spectral correction in these cases. So regarding multi-junction devices, it's important to mention that the junctions are series connected, so one of them limits the current. If you are using a flash simulator with the spectral distribution not very well matched to the real sun, you will have one of the junction limiting the current, and you will have a spectral mismatch that you cannot correct. So regarding bifacial PV modules, so how much power do I get from a bifacial PV module outdoor and the real field? So if we look at the specification, we don't have much more information, at least up to now, I think. We have seen some differences with the monofacial PV modules, like bifaciality. In these both cases are 70%. And we have here also a bifacial output rear side power gain, which says that if you are going to have a 5% gain, you will have this amount of watts, but it's just applying the 5%. So how do we measure the maximum power in the lab? First of all, we measure the IV curve applying 1,000 watt per square meter just to the front side. We don't apply anything to the rear side. Second step is apply the 1,000 watt per square meter only to the rear side, nothing to the front side. Then we calculate some coefficients which are called the bifaciality coefficients, which are defined in these equations. And then we do a couple of more of measurements simulating an rear irradiance on a front irradiance of 1,000 watt per square meter and a rear irradiance of 100 watt per square meter and 200 watt per square meter. So we can get a slope the slope of that straight line is called the BIFI, which is the real irradiance driven power gain yield, which means how much power, output power you will get from each watt per square meter that you are going to get from the rear side. And in the current draft for the 6.12.15 standard, the BNI, which is the bifacial nameplate irradiance, is being designed, which means like an STC for bifacial, which is 1,000 watt per square meter in the front and 135 watt per square meter in the rear side. So something about the uncertainties. The uncertainty is the parameter associated with the result of a measurement that characterizes the dispersion of the values that could reasonably be attributed to the measurement. What does that mean? That means that we don't really know which is the real value of a measurement. For example, that what we can know is just a range. For example, in this case, the maximum power of a module, for example, is 250 watt, plus minus 1.6%. This is the uncertainty. This means that the most probable value is 250, but the real value will be in this range of plus minus 1.6% in this example. This means that in this range, we have 95% of the probabilities that the real value is. So some uncertainty sources that just very briefly, because I haven't run out of time. There are some uncertainty sources. There are many uncertainty sources, but it's important is to know exactly how do you measure, how you are measuring the maximum power in this case, and analyze every single possible effect that your instrumentation can have. For example, you can have sources related to the irradiance, like the reference cell, like a lecture in the data acquisition system to the output, the temperature, the uniformity of the reference, the temperature of the reference cell, the uniformity of the light, and any possible spectral mismatch, any possible angular incident, or difference in the positioning of the reference cell with the plane of the sample. You can have some uncertainty sources related to the temperature. With the temperature probe, for example, the acquisition data that is going to read the output. There is a temperature uniformity in the module, and especially for outdoor measurements, there is a difference between the cell temperature and the substrate temperature, which is where you actually do the measurement. There are some uncertainties in the measurement, in the electrical measurements, like in everything. Another might be important source can be the corrections to STC, especially if you measure outdoor. You have to apply some equation. If you are using some parameters that are not very accurate, you can have different results. That's why, for example, the temperature coefficients or the series resistance are very important, because they can add quite a lot of uncertainty. And whatever other factor you can imagine, actually. Everything related to calibration, to drift, to resolutions of the equipment, to repetibilities, reproducibilities, differences in the electrical connections. And finally, some different aspects with the thin films are the ones related to the stability of the sample, related to the light-induced degradation, to the annealing, or to the dark storage that the modules. So the modules have to be preconditioned before the measurement. And I think everything's that. Thank you very much.
Thank you, Javi. Thank you, Ana Belén. We have been longer than expected, but we have time for some questions. There are some in the chat. The first one is from Antoine. To exhibit an open circuit, it is not clear what this means. I think this is for Ana Belén or Javi, if you want. This is about the pass-fail decision.
Yes. Can you hear me?
Yes.
Yes.
Okay. To exhibit an open circuit, yes, it was regarding the pass and fail criteria of the 6.12.15 standard, and it is related to the fact that during some climatic and mechanical tests, we have to continuously monitor the continuity of the internal circuit of the module. And during all the tests, we have to check that there is not any open circuit during the test. If some, for example, during the mechanical load, because of the load applied, maybe some cell breaks or some connector breaks, it will pose a risk for the performance of the module, and it would be a fail criteria for this design.
Okay.
It's okay. If you want more explanations, I can tell you later.
Yes, something I am going to go on with the questions because there are some. Somes, he asked about the impulse voltage test. Which is the value of voltage impressed on the modules?
It depends on the class of the module of the application, but it can be up to 16,000 volts, the value of the maximum voltage applied during this test, the highest value applied. It depends also on the maximum voltage system in which the module will operate. For 1,500 volts of maximum voltage system, the highest value of the impulse voltage test would be 60,000 volts.
There is another one from Somes. How do you perform the reverse current test?
Oh, the reverse current test, we have to place the module onto a rigid support and cover it with a tissue paper. And then we have to apply 135% times the value of the overcurrent protection of the module during 2 hours. And the module should not present any flame, or it should not burn. And also it has to fulfill the visual and the electrical insulation requirements after the test.
There is another question from Alex. This is about a PV module. If it is partially shadowed, could there be a test to provide some percentage functionality under such conditions? I don't know, it's a PV module partially shadowed from the design itself. I understand.
Here, can you talk?
Okay. Yeah, I try to think about the maximum power, the functionality, I guess. It depends on what is which is the shadow one. How is that affecting to each every single cell? So the modules in the cell are usually series connected. Now they are half cells, so they have 2 circuits in parallel. So depending where the shadow is, depending on how the module, the output will be influenced. So it depends in a lot of things. So it depends if it's from the design. I don't know. You will get it measuring that in a lab. If it's a shadow because it's installed behind the tree, you could go with an IV tracer and measure the IV curve, and you will see the result.
And also, I want to add that in the hotspot endurance test, we have to look first for the worst hotspot condition. And there, in the first part of the test, we have to shadow alternately each cell to check for each design what is the worst hotspot condition. How does the shadowing affects the PV module output power? So in this test, in the hotspot endurance test, we also check how the shadowing affects the module.
Okay. Another question from Antoine. Which tests bring the highest number of failures?
In general, from our experience, we have seen that the tests with humidity are the most complex to pass for PV modules. In the first edition of the standard, there was only a dry insulation pass criteria for the modules, but in the second edition, it was added the wet insulation resistance test, and a lot of designs failed this test initially because of some insulation faults in the junction box, or there were some paths where the humidity could enter into the module internal circuitry. So maybe in general, the ones with humidity.
Okay. And there is another question about if you have some suggestions about the future or evolution of the test. What are they going to?
The standardization groups are working a lot in the new standards, in the new editions of the standards, and the main changes that are currently being proposed are to introduce also a dynamic mechanical load in the qualification of the performance, and also the potential induced degradation is going to be a requirement of the standard. And there are many other variations in the test just to address the potential failures that have been discovered with the new designs that are coming to the market.
Okay. It seems there are no more questions. So we are going to finish the session. There's one question. Thank you, Alex. Okay, you can contact us directly for any further question about that. And I just wanted to remind you that we are going to have another 2 webinars this week, on Thursday and on Friday, same time. And the topics are on PV plant project development and on potential induced degradation on Thursday and on Friday, tomorrow and the day after tomorrow. So that's all. Thank you again to our presenters, Ana Belén, Javi.
Yep.
Thank you very much to all the participants for joining us, and see you tomorrow. Thank you. Bye.
Bye.
Thank you.
Everybody.
Bye-bye. Thank you.